Okay, so this is question number 29 of the Magnetic Fields homework booklet. So in question 29, what we have is we start off with a graph, and it shows how a sinusoidal alternating voltage, so we've got an alternating current, and this graph shows how this voltage varies with time when it's connected across a certain resistor. And we can see that basically it goes positive and negative again, so we've got an alternating current. So the very first thing we're asked to do is to calculate or state the peak-to-peak voltage. Well, the peak-to-peak voltage, as we remember from the last question, is basically the voltage from here up to here. So if we look at this, the peak voltage, which goes from here to here, is basically 64 volts, and the peak voltage here is 64 volts, so we've got 64 and 64, basically gives us 128 volts. That's worth 1 mark. We're then asked to work out or state what the peak voltage is. Well, the peak voltage, as we've seen, is just the distance from here to here, so that's half the peak to peak voltage. So we just multiply our answer, so we just divide our answer by 2, and that gives us 64 volts. So just doing that is worth 1 mark. We're then asked to calculate the root mean squared value of the alternating current. So root mean squared voltage is equal to the peak voltage divided by root 2. We've just worked out what the peak voltage is in the last part of the question because that was 64 volts. We divide it by root 2, and to 3 significant figures gives us 45.3 volts. So you get 1 mark for using the equation and putting the numbers incorrectly, 1 mark for the right answer. In part 4, we're asked to calculate the frequency of the alternating voltage and also give an appropriate unit. So we need to go back to our graph. So we're looking for the frequency. So the way we would do that is, first of all, we would calculate the time period from the graph, and then we would calculate the frequency. So if we go back to the graph, the time period is the amount of time it takes for one cycle of this electricity supply. So if we start here, one cycle is positive, negative, and back to where we started from. And on this graph, it's very convenient because one cycle is exactly 10 milliseconds. And don't forget the m, because if we just read this as 10 seconds, then we're going to be out by a factor of 1,000. So we have a time period of 10 milliseconds. So if we go back to our calculation, the time period is 10 milliseconds, which is 10 times 10 to the minus 3 seconds. And then to work out the frequency, it's simply 1 divided by the time period, which gives us 100. And because we're looking at a frequency, the unit is hertz. So our final answer is 100 hertz. You get 1 mark for actually reading off the time period from the graph. You get 1 mark for correctly calculating the 100. And then you get a 3rd mark for actually writing down the unit, which is hertz. For part B, we're then asked to go back to the graph and draw a line to show the DC voltage that gives the same rate of energy dissipation in R as produced by the alternating waveform. So there are 2 things that we need to know here. First of all, this rate of energy dissipation, or DC voltage that gives the same rate of energy dissipation, that's basically the definition of the root mean squared voltage. And we worked that out in a previous part of the question, which we'll have a look at in a sec. And then the second thing we need to know is actually what a DC voltage looks like on an oscilloscope. And again, as we've seen in kind of previous questions, if it's a DC voltage, it doesn't change direction. So our dot, or whatever, it will just go upwards. Now in this case, the time base is turned on, and so the dot will move across the screen. So we're just going to end up with a line that goes across the screen at a constant value. So if we go back up to the root mean squared voltage that we worked out, it was 45.3 volts. So what we're really doing is we will draw a line. We'll go up and we'll find 45 volts on here, and then it's just a straight line that goes across here. And if we do that, then that gives us the equivalent direct current voltage. That gives the same heating effect or same power dissipation as this sinusoidal source here. So you get 2 marks for this. You get 1 mark for basically drawing just a straight line across, and you get 1 mark for drawing it at the right place, so at approximately 45 volts. And again, you're given a tolerance of round about 1 millimetre. So the final part of this question, part C, we're then told we have an oscilloscope, and the screen's got 8 vertical and 10 horizontal divisions. We're asked to describe how you'd use the oscilloscope to display the same alternating waveform, which isn't necessarily clear in the question, but it's talking about the same waveform, but so that we can see 2 complete cycles. Well, again, if we go back to here, then we know that the time period for, or the time it takes to one cycle is basically 10 milliseconds. So to see two complete cycles on there, our oscilloscope will have to be set so that we can see 20 milliseconds all the way across. So because it's got 10 horizontal divisions, then you'd set each horizontal division, in other words the time base, you would set that to be 2 milliseconds, because then you've got each square would be worth 2 milliseconds. You've got 10 divisions or 10 squares, so you'd be able to fit 20 milliseconds on your screen. So the way you would phrase this is you would say, first, if you're going to describe fully how you're going to use this oscilloscope, what you'll do, you'll say you're going to connect the oscilloscope to the Y input. So you'll take your power source, you'll connect it to the Y input of your oscilloscope. You'll then adjust the time base so that each division is 2 milliseconds. And it has to be 2 milliseconds because we've got 10 horizontal divisions and we need to see 20 milliseconds altogether. And then after that, you would alter the Y gain so that you can actually see the peaks and trough. So you don't have to be as specific about the Y gain in this case as you do with the time base. So if you write any of those three things down, then you will get 3 marks. So that was question number 29 of the Magnetic Fields homework booklet.